Hello students, in this lecture I am going to discuss the EST which has come as in 2023 in TIT. So here this is the general discussion about the end semester test. So here the first question which was given as this. So you have given you have to consider the following LPP, right, as a primal problem, and the given problem was this. And in the first part, you have to write the dual of the LPP. That means we have to write the dual. So you can remember that concept which I have already discussed, that if you have maximizing problem, maximize CX subject to AX less than equal to B and X is greater than equal to Z. And if I have to write the dual of this, here will come, it will be my B transpose Y subject to the constraints will be, here A will be my A transpose Y, and here will come C and Y will be greater than equal to 0. So what I have told you, whatever the sign you will have over here, the opposite sign you will have in the variables for the dual problem, that is the opposite sign, and the sign which you have here for the variables, the same sign you have for your constraint. So if you, the problem given was also your maximizing problem, so if you have to write the dual of the LPP, so it will be my minimization Z subject to, this will be my minus 5y1 plus 3y2, right, subject to I will have constraint, that will my have, this will be 2y1 and plus 4y2, and this will be my 2y1 plus I am taking the transpose, this is 2y2, this is 5y1 plus 2y3, right, and here it will come 12, 10, 10, and you have to write the sign for your y1, y2 and y3. So if you sometimes forget, right, in this the trick part was that if you forget this criteria, that what it holds the sign, the next part it was given as, right, you have to find the optimal solution of dual problem using simplex method. Simplex methods means there will all have inequalities that is of less than equal to type, and obviously there is none of your variable which will be your restricted or that. So you can see, you can apply your mind that we have to apply your simplex method. That means there is no my b is negative. That means if I consider the concept like that, the sign of this is less than and it will remain the same. So it will be my less, it will be my less, it will be my less. The sign here was greater, so it will be opposite to this. And this will be opposite to this, and we have only two variables, so y1 is greater than equal to 0 and y2 is greater than equal to 0. So you have to apply your mind if you have forgotten that what sign you will have, because in the second part it is given that you have to find the optimal solution of your dual problem by using simplex method. So the second part is that you have to use your simplex method, so you have to convert it into the standard form, minus 5y1 plus 3y2 subject to 2y1 plus 4y2. I will have one slack variable here, right, and one slack variable here. It will have 12, 10, and 10. And the same, this is 2y1 plus 2y2, and this is 5y1 plus 2y2, and all my variables y1, y2, and S1, S2, S3, that is coming out to be or greater than equal to 0. This is 0 into S1, 0 into S2, 0 into S3. So the table, optimal table, which was coming here for this solution, it was, so here you have to write your Zj minus Cj. You have variables as your y1, y2, S1, S2, S3. Then you have xb, or you can say solution, right? Here you write the Zj minus Cj values. And if you construct the table, it will be like this. So initially you have to take the basic variable as your S1, S2, S3. So this is your basic variable S1, S2, S3. So the corresponding, this is 2, 2, 5. This is 4, 2, 2. This is 1, 0, 0, 0, 1, 0, 0, 0, 1. And here you have right hand side 12, 10, 10. And this is coming out to be your 5, right? This is minus 3. If you revert the sign, this is 0, 0, 0 and 0. If you take this was becoming your pivot and pivot element. So when you apply the next iteration, so this will leave and this will enter. So this, the next iteration was coming out to be S1, S2, Y1. This is coming out to be 0, 0, 1. This will be your 16 by 5. This is coming out to be your 6 by 5, 2 by 5. And this is coming out to be your 1, 0, 0, 0, 1, 0. This is minus 2 by 5. And here it is minus 2 by 5, 1 by 5. And it is 8, 6, 2. And your Zj minus Cj values are coming out to be your so your Zj Cj values are coming out to be, I can write it over here. So this is the entry for Zj minus Cj. It is coming out to be your 0, minus 5. This was coming out to be 0, 0, minus 1. Since all your optimality has been achieved because all my Zj Cj are less than equal to 0 and this is the case of minimization. So this is coming out to be your minus 10. So what you got optimal solution as y1 as my 2, y2 is my 0 and my z star, that is the minimum z star value, is my minus 10. And you have also given that you have to show something related to your primal problem, and hence you have to show that using duality theory the maximum value of z cannot exceed minus 10. So if you remember your weak duality theorem, you have already done, right? So by weak duality theorem, if I am taking x as my x1, x2, x3, any feasible solution, and feasible solution for my primal problem, and primal is my maximized problem. And you remember that your C transpose X is less than always of maximization. It will be less than equal to your B transpose Y. So because if you take any feasible solution, you can take any feasible solution if you are taking even X0. So it will remain your maximum value, that is your C transpose X, because your B transpose Y is coming out to be your minus 10. So it will always less than equal to your minus 10 because this is my optimal solution. Therefore, your maximum value cannot exceed by minus 10. So this was the first question and first part. Next, you have given the second part, which was that you have to solve the linear programming problem by your integer linear programming problem by branch and bound method. So this was the question. So here you have to apply your branch and bound methods. So when you will solve this question, this is your maximize z 4x1 plus 5x2. This you can even solve graphically. If you will solve it graphically, the solution is coming out to be your x1 is equal to 4 and x2 is coming out to be your 3 by 2 and the z value is coming out to be your 47 by 2. So it clearly has this value as integer. So you can break this in two branches, that is x2. So this is 1 point something. So it will be either less than equal to 1 or you can have the constraint greater than equal to 1. So if you will add this constraint, So the reason that optimal solution which you got, this is 10/3 and you got x2 as 1 and your z value was 55/3. And if you break this and if you apply this constraint on the given problem, which was earlier, you have two constraint, one more constraint if you will apply, you will get x1 is equal to 2, x2 is equal to 2, and you got z as your maximum value, that is your 18. But still here, your value is greater than 18, so you have to break this. This is 3 point something, right? So you will apply x, this is 10/3, that is 10/3, that is 3 point something. So x1 is either less than equal to 3 or x1 is greater than equal to 4. So if you will apply this, x1 is coming out to be your 3, x2 is coming out to be your 1, and z was coming out to be your 17. And for this, you will have your infeasible solution if you have applied. So you can notice here, even this came out to be your 17, 3/2 something. You should not proceed from here because you have earlier also got the value as 18 and here value is 17 point something, which was lesser than this. That means the optimal solution is this one. So x1 was your 2, x2 was your 2, and your z value is coming out to be your 18. So this is my optimal solution and optimal value. The third, which was given to you have to draw the network. So for drawing the network, you have to always take care what is given, that you take care of your dummy activity which you have to add. So the third question was this, that you have to draw the network. So you know, when you have to start your A, you does not require any predecessor. So if I have to start the A activity, I do not require any predecessor. So it can be started from this. This is the first. For starting the activity B and C, I require my A activity. This can be my activity B and this can be activity C. And to start the activity E, I require B and C. So you can notice over here, you cannot end this like this. You can start the activity. So here you have to create what you have to create your dummy activity, right? That you have to look for the direction, which direction you have to take. So in for further, you also require B. That means the direction for the dummy activity should be towards this. So this is my activity E. And also to start the activity D, I require only activity B. And to start the activity, sorry, this is D. To start the activity F, you also require activity B. So this can be my D activity and this can be my D activity. This can be my F activity. And next what you have to see, that to draw the activity G, you require D and D together. So this can be this. So this can be your G activity. And to start the activity H, you require F and G. So this can be this. So now F and G both are required for this. Next, you have I activity for which you require B and C. So you remember here your B and C also end. So you can start your I activity from here, which your end starts with this. This is your I activity. To start the activity J, I require I and H together. So this is my J activity for which I need to require this is. So this completes your drawing of the network, so that you have to see what is given to you. Next, the second question was given to you related to your transportation and assignment problem. So you have given the question that you have three jobs and you have 4 machines. So whenever you have to apply your Hungarian method. Firstly, I always say that firstly you have to check that it is problem for minimizing the cost. Yes, it is not given anything regarding to that. So that means this is my minimization next, but you have to check that it should be my balanced problem. So for the balanced, I have here 4 columns, but three rows. That means I have to make it balanced. So this is my J1, J2, J3, and this is my M1, M2, M3, and M4. So I have to add my fourth job, that is my dummy job. So here this will be my 20, 25. This is given as 22, 28, and this is coming out to be your 15, 18, 23, 17, 19. This was 17, 21. Because here is dash, that means this you cannot assign job. So this is my infinity, and in this I have to reduce it into this. So this was my assignment problem. I have to apply now my Hungarian method. So firstly you have to convert it into your row minima. Row minima means you have to consider the minimum element from the rows. So this was coming out to be your 0, 5, 2, 8, and this was your 0, 3, 8, 2. This was coming out to be your 2, 0, 4, infinity, and this is coming out to be your 0, 0, 0, 0. Next, again, you have to take the column minima. This is my row minima. And then you have to go for your column minima. In this column will not change, right? And in this, so in every, you can see in every column there is a 0. So this matrix remains same, 5, 3, 0, 0. This will be 2, 8, 4, 0, and this will be 8 to infinity. This is 0. So next, what you have to draw? You have to draw the minimum number of horizontal or vertical lines so that your all zeros should be covered. So if I draw like this is my one vertical line. If I draw this, and this is my one vertical line. So these all are the zeros. These are the lines. The 3 lines I have drawn, but the order of the matrix is of 4. That means which is not equal. So that means I have to subtract the minimum element from the uncovered element. So this matrix will become, this is 0, 3, 0, 6, and this you have 0, 1, 6. This you have again 0, 4, 0, 4, infinity. This you have 2, 0, 0, 0. Next, what it is this? Now, you have to again draw the minimum number of horizontal and vertical lines. So if you draw line this, draw line this, draw line this, and draw line this. So these are your lines. So that means now you can do your assignment, because the lines drawn are the same as the order of the matrix. So now you can start your assignment. So how I have told you that you have to firstly look for that row in which there is only 1 0. So this is the second part also answers over here. You do not have any row where has only 1 0. In every row there are more than or 2 zeros. So you can see from here whatever assignment you will create, it will have your alternate optimal solution. So if I am assigning this value 0, so this will be cancel out, right? And this will be cancel out. So this can be assigned as 0, and this can be assigned as this 0. This can be assigned over here, and this will be cancel out. This will be this. So this is my first assignment in which I have assigned J1 as my M1, J2 as my M4, J3 as my M2, and J4 I have assigned as my M3. So if you sum over the cost, this is 20, 17, 0. The sum of the cost is 54. And the second is asking Does this problem have more than one optimal solution? That what I have told you, that in every row you have zeros. So for selecting this zero, you have like selected this zero, you can also select the other zeros. Then you will have more than one optimal solution, and that you have to find, right? So I'm doing the assignment over here and I'm making change in this. So this was 0 over here in infinity. Suppose like I have assigned this, suppose I have assigned this job to this machine. So this was cancel out and this was cancel out, and this is my next assignment. Suppose I am doing this is cancel out, right? And I am assigning suppose this as the same this, and this will be cancel out like this. So here you have assigned, changed the assignment, that J1 was your M3, J2 is your M1, J3 is your M2, and J4 is your M4. So even if you sum over the costs now, this is 22, 15, 17 and 0. If you sum over this is also the same cost is coming. That means this is more than one optimal solution, right? So this was your second question. The third question only, it was a simple question, but the trick part was given in, some students got confused that what is given, but it was given nothing. The problem which was given is, this was your actual problem which was given to you, that you have transportation problem in which you have three sources and you have 4 destination. So what you have to check, whenever you have to apply any your initial basic feasible solution, here you have to use your Vogel's approximation. First and foremost thing, you have to check that it should be minimizations, yes, that if the costs were given. Next, what you have to check, you have to check that it is balanced or not. So if you check it was not your balanced transportation problem, and this was not balanced. So what is the issue, that if you take 19, so this was coming out to be your 90, and this was coming out to be your 65, that means it is not balanced. What was the trick part over here? That means it was already given that find the optimal solution of transportation if the penalties per unit cost for the unsatisfied demand. So you can see here your demand is not satisfied and the costs were 215. So whenever you have to create a dummy entry in this, you should not be take 000 because the penalties are already given, that you have to take 215 to make it balanced. So this was coming out, only this was the trick part. So some students might not have used this and you use dummy as 000. So when you will do your Vogel's approximation, so the assignment here was coming out to be your 18, right? And here assignment was coming out to be your 1. Here your assignment was coming out to be your 25. Here the assignment is coming out to be your 30. And here the assignment was coming out to be your 4. So you have 1, 2, 3, 4, 5. This is 3 plus 1, 4 plus 3, 7. So you should have 6 assignments. So you have over here 18, 1, 2, 3, 4, 5, and so this is 18, 1. This is coming out to be 25. And here it was assignment 1 more. This is your 12. So this was the assignment which you got by Vogel's approximation. So when you got, that means you got your minimum cost for your initial basic feasible solution. That was coming out to be your 18 into 3 plus 1 into 6 plus 12 into 4 plus 1 into 25 plus 4 into 4 plus 30 into 7. So this was your initial basic feasible solution cost, and this was giving out to be 359. And you have to find the optimal solution. So this is your initial basic feasible solution. For optimal solution, you have to assign U1, U2, and U3 over here. V1, V2, V3, and V4 over here. So if you assign 0 over here, U2 was coming out to be 1. This is 1. This is your 3. 3. This is coming out to be 6, and this is coming out to be your 0. So this entry was coming out to be your -2. This entry was coming out to be your -2, and this entry was coming out to be your -3. This entry was your -2. This entry was coming out to be your 0, and this entry was coming out to be your -4. That means your all southwest entry, if you see, all are your less than equal to 0. That means this is the solution which you have obtained. This is my nothing. This is my optimal solution, and this is my minimum value of z. So your optimal solution is x11 is your x12 is 18, x13 is 1, x21 is your 12, x24 is your 25, x31 is your 4, and x33 is your 30. So this was the solution, and your all our southwest entries are 0. The second part was that, does this problem have more than one optimal solution? That means if any southwest entry is 0, that we actually got this is 0, that means this and this has more than one optimal solution. So this has 0. So you have to assign over theta over here, and you have to create a loop. So this is theta, and you can go now in this direction. Here you have already one, this, and you can come like this. So this is 18 minus theta, this will be plus theta, and this is minus theta. So theta, if you assign the minimum value of 18 and 30, so it was coming out to be your 18, and then your assignment changes. So what your assignment is, so I'm making a change in this. In the last, you got over here, this is your 18, and this 18 will be cancelled out from this entry. This is 1 plus 18, this will become my 19. And here, this entry will be 30 minus 18, and this will become my 12. So this is your solution in which your optimal assignment has been changed. That means now you have assignment x13, this is same, x13 is 18, 19, x21 is your 12, x24 is your 25, x31 is your 4, x32 is your 18, and x33 is your 12, and you have got the same answer, that is your 359. So this was your second question, and next you have the question, third question was given to you. So the third question was also related to your project management problem. So you have some given activities and all the normal cost and normal duration. You have to use the critical method. So firstly, to start with this, you have to firstly create the network. So this is your first activity, 1 to 2 activity, and this is your 1 to 3 activity. 1 to 4 activity was given, and then you have to given the activity from 2 to 5, right? And you have given the activity from 3 to 5. You have given the activity from 4 to 6, and you have also given the activity from 3 to 6, and this was given as from 5 to 7 it was given, and 6 to 7 it was given. So the cost here was given as 7. This was 5. The normal days, that is 8, 9. This is 5. And this is coming out to be your 6. This is 7, 3, 2. And you have to, firstly, when you have to use critical method, path method, you have to find your ESJ, latest completion and earlier starting time. So this was coming out to be your 0. This was 7. This is coming out to be 8. This was coming out to be your 15. And this was coming out to be your 16. This was coming out to be your 5. And this was coming out to be your 18. So this is 18. If you take the reversal, it is coming out to be 16, 15, 8. This is coming out to be your 9. This is 7. This is coming out to be your 0. So you have to use critical path method. So the first thing is that project will complete in the normal duration is, that is your 18 weeks, because the weeks as are given to you. So normal cost, always the student do the mistake that they take the sum of the critical path, but in not critical path, in normal cost, we have to take the sum of all the cost of the activities. So it was coming out to be your 6,500. Now you have to use critical path. You have found for the first part what is the normal duration and normal cost, that you are done. Now you have to determine the optimal cost for completing the project if the normal duration is to be reduced by 2 weeks. That means we have to reduce 2 days. So we have to check from where we can reduce. So you can notice in this case, this is my critical activity. And the one path was 1 to 5 and 5 to 7, and one path was also this 1 to 4, 4 to 6, and 6 to 7. So here you have got two paths, 1 to 5, 5 to 7, and 1 to 4, 4 to 6, and 6 to 7. So whenever you got more than one path, so that means you have to reduce from both the paths. Reduce days, or because here we are weeks, from both the paths, right? Here it is not any common activity that we can say so that we can find the slope. That means we have to find the slope now for both the paths. So this, for this activity, the slope was coming out to be 50, and for 2 to 5 activity, the slope was coming out to be your 225, and for 5 to 7 activity, the slope was 100. So for this path, the slope of 1 to 2 is minimum. That means whenever we have to reduce from 1 to 2, and simultaneously from 1 to 4, the cost was 200, slope was 200. 4 to 6, the slope was 125, and 6 to 7, the slope was 350. So that means the minimum here is your 4 to 6, because there is no common path. So we have to reduce the days or the weeks from the activity 1 to 4, 1 to 2, and 4 to 6 simultaneously. You cannot do like this, that you can reduce from one activity. No. For reducing the activity, for this activity, you have to check the crash limit, right? So for this activity, this was coming out to be, the crash limit was coming out to be your 3, and for this crash limit was coming out to be your 2, right? And next, for finding reduce number of weeks, so we have to find the compression limit. The compression limit, that means your crash limits and your free float. If you calculate your free float for your non-critical activities, the free float, this is your non-critical activity. The free float was coming out to be 0 for this activity. The free float was 6 for this activity. And the free float is coming out to be your 4 for this activity. That means the free float, that is, you have to take the minimum. So that's, you have to do the compression by 2 weeks. So you can compress by 2 weeks. Either you form the network in the last, or you not, right? So that means it will reduce the cost by 2 weeks. And what will be your cost? So crash cost will be 6,500. You are reducing 2 days from the activity 1 to 2, whose slope is 50, and 4 to 6 whose slope is 125. So the answer was 6850. So if you have to reduce, so you have to reduce, this will be my 7 minus 2. And I have to reduce here from, this is 5 star, right? So this is 5 and all your EST, ESJ and LSJ will change, right? So this was only your third question. And the third B part was, so the third B part was for the multi-objective problem. So for that, whenever efficient solution, efficient frontier mean, what you have to do, you have to create your feasible region. For a feasible region, you have constraint 3x1 plus 4x2. For this, you will get your point as 1 as your 4, 0. And this is coming out to be your 0, 3 if you join them via line. So this was your feasible region. And these are your, because we have LPP, so it will lie on the 3 are my corner point. So 1, I have objective function is that your x1 plus 9x2. One objective function is 2x1 minus x2. The third objective function is 17.5 x1 plus x2. You have point as 0, 0, the point as 4, 0, and you have point as 0, 3. So if you substitute the 0, 0 in this, and if you substitute 4, 0 in all these objective function and 0, 3, you will get as 27 minus 3 and 3. Now the first objective function was to maximize this. So what is the maximum value from these 3 points? This is giving me maximum value. The second objective function was minimize. So the minimized value I got over here. This is my minimum for the second value, second objective. Third is maximize. So this is giving me my maximum value, right? So now that means you got 2 points, that is 0, 3 and 4, 0, which are satisfying your objective function. That means these are my efficient solutions. And I have told you the CLC for this is your efficient frontier. And the condition on A1 and A2, that your A1 plus A2, that is coming out to be your 1, and A1 and A2 should be greater than equal to 0, right? So this becomes your efficient frontier. The fourth question was related to your non-linear programming problem. So this was your fourth question, that you have to minimize the function and you have to use the steepest descent technique. So if you can apply that I have told you, for the first iteration, you have to take x1, 0, 0, and you have to find del f, that is your curl f by curl x1 and your curl f by curl x2, right? So when you have to find curl f1 by curl, so this was coming out to be r1 4x1 plus 2x2, right? And this was minus 1 plus 2x1 plus 2x2, right? So whenever you have to find the next iteration, x2, what was your that? x1 minus lambda times your this del at fx1, right? So when you found, this was coming out to be your lambda 1 square minus 2 lambda 1. So when you have to substitute this point and this point, when you solve this and you have to do curl f by curl, lambda equal to 0 and lambda was coming out to be your 1 value. So your x2 point you got here as minus 1 and 1. And when you proceed and have to check f of x2 minus f of x1, in this case, this was your minus 1 minus 0, which was not less than 0.5. So that means you have to perform the second iteration. In the second iteration, you got the point as your minus 4 by 5 and 6 by 5. So when you check here this condition that your f of x3 minus f of x2, So that was coming out to be your 0.2, which is less than 0.5. That means this is my optimal solution, and my minimum value, that is my optimal value, I'll substitute x1 as minus 4 by 5, x2 as 6 by 5. So this was coming out to be your minus 1.2, and x1 is your minus 4 by 5, and your x2 is your 6 by 5. The second part was given that the question is that you have to check for the function which is given to you, that it is, you have to find the stationary point. The stationary point, the necessary and sufficient, that condition you can find that you could take the partial derivative equal to 0. When you take the partial derivative equal to 0, it gave you x1 equal to 1 and it gives you x2 equal to 9 by 8. So you got the point 1 and 9 by 8 as your stationary point. Now you have to check that is this maxima or minima. So you can check by the Hessian matrix that you can create, right? So your Hessian matrix was coming out to be your minus 4, 0, 0, minus 8. So your D1, the determinant is minus 4, which is less than 0. D2, that is coming out to be the determinant of this. This is coming out to be 32, which is greater than 0. That means H is my negative definite. If my matrix is negative, that means the point which I got 1 by 9 by 8 is the point of maxima. So this is the point of maxima, and you have to check further it is global or optimal. So I have told you, whenever your Hessian matrix is either positive definite or negative definite. So negative definite, man, that means that your F is concave, right? So F any, that means, and it is of maximum case, F is concave. F is concave, that means if your F is concave, that which will give my, yes, the point 1, 9 by 8 is the optimal and global, right? So it will be global optimum, right? So the third part, the third was that you have given, you have to solve NLPP by KKT condition. So that I have already told you, could create your Lagrange function. So this was 0.4 x1 square plus 0.2 x2 square minus 3.6 x1 minus 1.6 x2. But whenever you have to apply your KKT, the first and the foremost, you have to check that the given function, because the given function was of minimization z, that means the function f should be my convex function. So how you can check convex function? You create your Hessian matrix. It was coming out to be your 0.4, 0.8, 0, 0, 0.4. So your first D1 is greater than 0, D2 is also greater than 0. So your H is positive definite. So which implies my F is convex, which is done. And the constraint here was your constraint was 2x1 plus x2 less than equal to 10, and this is my closed half space. So yes, this is my convex. So yes, the given programming problem is my convex programming problem. So then I can apply my KKT condition. For KKT condition, I have to create the Lagrange's function. Whenever I have to create Lagrange, so what are the necessary condition? Curl L by curl x1 equal to 0, curl L by curl x2 equal to 0. The second is that GIX, that means lambda 1, when you will create plus lambda into the first constraint 2x1 plus x2 minus, it was your 10, right? So lambda times 2x1 plus x2 minus 10, it should be equal to 0. That means you can also understand, I have also told you that this is del of f, right? Plus you take L of GIX. minus bi also equal to 0. This constraint is lambda I times gix minus bi equal to 0. The third condition that you have to take, gix should be less than equal to bi, which was your 2x1 plus x2, that should be less than equal to 10, because this is the minimum problem and you have considered plus lambda over here, then lambda should be greater than equal to 0, right? So whenever you will take curl L by curl x1 equal to 0, this will give you the condition. The first A condition was 0.8 x1 minus 3.6 plus 2 lambda equal to 0. And from the second, this is A part, first 1A and 1B, that will be curl L by curl x2 equal to 0.4 x2 minus 1.6 plus lambda equal to 0. The second condition is this. So I have told you, you have to consider once lambda equal to 0, 1, take 2x1 plus x2 minus 10 equal to 0. If you consider lambda equal to 0 and you substitute, this is my 1a and this is my 1b. So you got the point here as x1 as 1.4.5, x2 as 4. But if you substitute in this constraint, third constraint was not satisfied. That means this cannot be my solution. So you have to consider this. So this you have to take 0. So when you have to take this as 0 and you will solve 1a and 1b. So x1 was coming out to be your 3.5. x2 was coming out to be your 3. And lambda was coming out to be your 0.4. And for this also your constraint 3 is satisfied. Lambda is greater than 0. That is satisfied. That means my x1 is your 3.5 and x2 is my 3, and the z value, that is the minimum value, is coming out to be minus 10.7. This was all about your EST. Okay, good luck for your future. Thank you.